Okay, so in this video, we're going to be taking a look at systematic errors. And we're specifically going to look at how systematic errors affect graphs. So initially, we'll take a look at how they affect linear graphs, but my main focus of this video is how systematic errors affect non-linear graphs. So where we've got inversely proportional relationships, quadratics, inverse squares, those kind of things. So, what do we mean by systematic error? So, it's a predictable decrease in the accuracy of a reading. So, essentially, maybe when we're measuring a distance, we always measure the length to be 5 centimeters longer than it's supposed to be. Or a time, we're always measuring the time to be zero point 0.2 seconds shorter than it's supposed to be. So it's predictable because it's the same value in all of them, but it will have the effect of decreasing your accuracy because it's taking you away from the true reading of what you're trying to get to. So let's take an example where systematic errors will come up. So this is a standard experiment we do at A level or pre-U, whatever you do. It's where we measure the light intensity at different distances from a bulb to see how they're related. This is actually an example of an inverse square type relationship. So quite often what happens is we introduce a systematic error. So this is fairly unavoidable. We can make guesses as to how big our systematic error is, but essentially we can only measure from the light meter to the edge of the bulb, if you like. There's going to be a systematic error for the distance between the edge of the bulb and the actual thing generating the light, the filament here. And I've shown that on here. So this is our systematic error. Now, in the experiment, we might be able to make a guess at how long this distance is, but we're likely to not have guessed correctly, so we're going to introduce some sort of systematic error. Okay, so this is where one might crop up. So let's have a look at how it affects linear type relationships. So I've got a spreadsheet where we can do this. So essentially, what I've got on here is I've got some parameters that I can change. So I can give myself a different gradient of the graph if I want. I can give myself a y-intercept on here if I want. But I'm just going to set them back to where they were, just because I've seen this work already with this data. So what we can do is we can introduce a systematic error in our independent variable, or in our I, or we can introduce a systematic error in our D, and that's what all of this data over here is calculating. So let's see what a systematic error in I looks like. So let's increase this one to 1. So if you're paying attention, what you can see is we've shifted the graph to the right by 1. So if we put in a 5 here, you can see that we've shifted this graph across to the right by 5. If we do -5, we can see with it, if it's negative, so we're measuring in the other, like instead of measuring too small, we're measuring too big, etc. We can see we've shifted to now to the left by 5 instead. So a systematic error in I, or a systematic error in whatever you're plotting on the x-axis, is going to shift your graph left and right. That's hopefully not too surprising. If we do it in D, or to whatever's on the y-axis, you can see that we shift the graph up by whatever the amount is. So the bigger we make that amount, the more we'd shift our graph up. Or if we put in negative values, we can shift the graph down. So systematic errors wouldn't have any effect on the gradient of this graph. So let's say we're using the gradient to determine a value. Systematic errors wouldn't really matter because all they do is shift it up, down, left, or right. They don't actually change the gradient, so we wouldn't have to worry about them too much in an experiment. So if we go back to OneNote, so that's what we've just seen. So if we've got a linear or a straight line type relationship, systematic errors just cause a what we call a translation. So taking the object, shifting it to the right or left or up or down, but not actually changing it. So we're not changing its gradient, we're not changing its shape or anything like that. So we don't have to worry about those too much with straight line type relationships. We do have to, however, have to worry about them with non-linear type relationships. So let's take a look at that. So let's say we're investigating inversely proportional relationships. So maybe we've done some research before doing an experiment, and we know that we should find an inversely proportional relationship between our independent variable, our I, and our dependent variable, D. So the general equation for the an inversely proportional relationship is if we multiply I by d, it should give us a fixed value or a constant the whole time. So we can test whether this is accurate by plotting two different graphs. We could plot d against 1 over I, or we could plot 1 over d against I. If it's an inversely proportional relationship, either of these two graphs should come out as a straight line through the origin, and the gradient of them can be used to determine what this value of k is. If you want some more detail on that, I released a video previously looking at this process of generating these graphs in more detail, so do check that out if you haven't seen that. Okay, so look, at the moment we've got these two graphs and neither is better than the other, at least from a theoretical standpoint. But actually, from when we start thinking about systematic errors, actually one of these two graphs will be better than the other. So let's go back to the spreadsheet so we can see that. So if we go to our inversely proportional one, so you can see I've plotted a graph of 1 over d against I. And what we're going to do is see how a systematic error affects this graph. So let's try one in x first of all. So, let's say our independent variable, whatever it is, has a systematic error of 5. And you can see it behaves in exactly the same way. Because we've just plotted I on this axis, it shifts it either to the right if it's positive or to the left if it's negative. No big deal at all. Okay, so let's set that back to 0. Let's now see what happens if we introduce a systematic error in D. And remember, we're plotting 1 over D here. So let's put in 2. So you can see that what we've actually done, so blue, we've actually changed the gradient of it completely. The gradient's gone from being positive to negative. And if we change our value around some more, we can say we completely changed the line. So the fact that there's a systematic error in D has a really profound change on this graph. So because we're using the gradient of this graph to determine K, if we have a systematic error in I, that's not a problem because it doesn't change the gradient, so that's fine. But if we have a systematic error in D, that actually changes the gradient and changes that value of the constant, so that could be crucial. So what this means is we have to make a decision when we're plotting our graph of which of our variables we think are likely to be affected by systematic errors. So if we go back to this one, so we started off by looking at this experiment here, where changing the distance and measuring the light intensity. So theory says that they should follow an inverse square law. So what that means is that the light intensity multiplied by distance squared should give you a constant value. So we said that there's likely to be a systematic error in D. So that means we're going to want to make sure that on our x-axis, because D is our independent variable, that's the thing we're going to change, and we'll measure the light in the light intensity depending on that. So this is going to be on our x-axis. So that's why I'm just plotting D here. I've chosen this equation here because it allows us to just plot D, and then we have 1 over root I on this left-hand side. If, however, we thought maybe the systematic error might be in I, then we would have to make sure we plotted I over here on the left-hand side and had sort of 1 over d squared on the left. But since we can eliminate all other sources of light in our room by using blinds and turning off the light, we're far more likely to be affected by this systematic error in here. So we're going to plot d by itself. But this is something to make sure that you consider when you're doing experiments. If you're dealing with nonlinear graphs, which we're going to be doing quite a lot now we're at A-level pre-U kind of standard, you have to really think about the graph you're going to plot in terms of systematic errors, because some experiments have them that you really can't do too much about, and so you have to make a sensible decision about what graph you should be plotting.